Previously, we defined an almost complex structure on a finite-dimensional real vector space V, and then we show how that's equivalent to giving a complex vector space structure on V. At the end of the video, we remarked that any almost complex structure I on V always induces a linear operator on the complexification of V, which we'll also denote by I. Here this I is supposed to be complex linear. In this video, we want to decompose this complexification of V into eigenspaces of this almost complex structure I. To do that, first we need to ask, what are the eigenvalues of I? Now, how do we usually find eigenvalues? Well, we look at the characteristic polynomial, right? So what's the characteristic polynomial of I? Well, from this description, we see that the characteristic polynomial of I must be x squared plus 1. Thus, big I has eigenvalues plus or minus this little I. Now, let V10 denote the eigenspace corresponding to this eigenvalue I, and V01 be the eigenspace corresponding to the eigenvalue minus I. Then we claim that we have a direct sum decomposition, and that these two subspaces are actually conjugates. In other words, the conjugation map on this complexification map one of this space onto the other. So let's see why that is. First of all, because these two spaces are eigenspaces correspond to two different eigenvalues, so they obviously must intersect trivially. So that part is easy. Now let's see why they actually span this complexification. That is because every vector v in this complexification can be written as the following sum. And this part lies in the eigenspace corresponding to the eigenvalue I, whereas this part lies in the eigenspace corresponding to the eigenvalue minus I. You can check that by directly applying this linear operator. If you apply this big I onto this, we'll get this, which is just this expression, and then multiply with I. So this is indeed an eigenvector corresponding to this eigenvalue little I. And similarly, you can check that this is an eigenvector corresponding to the eigenvalue minus I. So that gives this decomposition of this complexification. Now let's check why conjugation takes one factor into the other. To that end, let us write this V as x plus iy. Then in that case, its 1, 0 component can be rewritten as... Now we can expand this because this big I is supposed to be complex linear. So it's linear over C. We can then collect the real part and the imaginary part and get the following. In particular, its conjugation is gonna be... And this clearly lies in the 0, 1 component. So conjugation maps v1, 0 into v of 0, 1 and vice versa. Now we want to make a warning. So far we have two complex vector space structures on this complexification. We have a complex vector space structure given by I, and one is given by this big I. We have to be careful about distinguishing them because they coincide on this v1, 0, but they do not coincide on this v0, 1. So they agree on the first component here, but they actually differ by a sign on this component here. Let's actually check that. So let's first apply both of these to the first component here. Little I times v is iv, and then little I times minus little I is equal to 1. So here we get iv plus this big iv. On the other hand here, this big I of v is just big I of v, and big I times big I is minus identity. So here we just get plus iv, and we see that these two results are the same. So now let's see what happens when we apply both of these to the second component. Here when we apply this little I, we have to this v we have little iv, and then here little I times little I is minus 1, so this is minus of big I v. Here when we apply this big I to little v, we get this big iv, and when we apply this big I to this term, we know that big I squared is minus identity, so we have this minus iv, and we see here that these have opposite signs. So these two different complex structures do not agree on this v0,1 component, so let's be careful. In what follows, we are gonna work with the vector space structure on this complexification given by this letter I. The particular application of this decomposition in this course is to decompose the complex tangent space of a complex manifold into the following components. We'll discuss that more in later video.